Okay, good morning, class. So today, yesterday, so we have discussed what is numerical method. All right. So means that we are using a few methods to find the roots or to solve the equation that we cannot solve by using algebraic method. Huh? And we mentioned three methods: graphical, iterative, and Newton-Raphson, right? So as I said, graphical method means you draw the graph on the graph paper, then from the graph you find the approximate roots. And the other two method is iterative and Newton-Raphson. And also I have told you that before we use these two methods, iterative and Newton-Raphson, these are the two things that you should know that will come up in STPM very often. One is to show that the equation has at least one root. Remember, we need the graph and find how many intersection points. And second one is to show that there is at least one real root lies between two numbers, two integers. So we have to find FA and FB and show that they have opposite sign. So memorize this sentence so that you can write the conclusion correctly. Okay, so today we will go to see what is iterative method, or we call it method of iteration. All right, iterative method is a repetitive process. Means we repeat the same calculation by using the same formula, which attempts to solve a problem by finding successive approximations to the starting from an initial guess until the required degree of accuracy is achieved. Means that we will start from one initial value of x that we guess is very close to the roots, right? Then by using the same formula, we are going to repeat the same formula and calculation so that we will get a series of the value of x, which is closer and closer to the actual roots. All right, so this is the meaning of this sentence. All right, an approximation to the root of the equation fx equals 0 can be found by using this method if the equation can be rearranged into this form. Let's say you are given one equation fx equals 0, and this equation can be rearranged in this form. This form means left hand side only x. Other terms will shift to the right hand side. Then the root of the equation fx equals 0, or the root of x equals gx, is the value of x at the intersection points of the graph of y equals x and y equals gx. Okay, so is therefore the root is the value of x at the intersection point of the graph y equals x. So y equals x is the left hand side, okay, and y equals fx. Remember yesterday we have discussed, right? To find how many roots, we arrange the function into these two so that it's easier for us to draw, right? That one is for any function. But to use iterative method, it must be in this form. All right, it must be left hand side only x, and right hand side is another function in x. All right, so we will have line y equals x and y equals gx. And this iterative method only valid, means we only can use this iterative method to find the approximation of x if the modulus of g prime x is less than 1. This statement is very important. All right, the modulus of g prime x is less than 1. Means we have to differentiate gx and get g prime x. Then we sub in the first initial value. Remember just now we say we guess one initial value, right? We sub this first initial value into the g prime, and if the modulus of the value is less than 1, then means that we can use this iterative method to find the approximate root. If it is the modulus of g prime x is not less than 1, means more than 1, then it's not valid. Okay, so the following step we will explain why g prime x must be less than 1. Okay, this is the step that we are going to use iterative method. All right, so yeah, I draw one very big one so that you can see clearer here. All right, so you see the step is, first, let's say I arrange, let's say you are given one equation fx equals 0. All right, then I rearrange it into the form x equals gx. So I have two function or two graphs lah. One is y equals x, which is this straight line. Alright, so remember lah, if it is line y equals x, means the gradient will be equals to 1. Alright, remember the g prime x, modulus of g prime x 1. Okay, then another side gx is a curve lah, let's say. Alright, let's say the root, the actual root of this function is alpha, means the intersection point lah. Alright, means the intersection point. This is the actual root. Alright, alpha will be the actual root or the intersection point of it. Okay, then we will take x1. We will just choose one value of x which is close to the actual root alpha to be the first approximation to the root. So the line x equals x1 will meet the curve at point P with coordinate x1, gx1. Okay, so let's say we choose x1, which is very close to the actual root alpha. Alright, so we draw a line from x1 to the curve. So this is point P lah. Alright, and the coordinate for point P is x1, gx1. Correct, right? This is x1. The x coordinate is x1, and the y coordinate is gx1. And the y coordinate is gx1, right? So this is point P. Alright, so which is second step. Okay, now next, draw a horizontal line from P to meet the line x equals alpha at Q and y equals x at R with this coordinate. Alright, so it means that from point P, we draw a horizontal line like this lah. We draw a horizontal line which will meet the line x equals alpha, means this line lah. This is line x equals alpha. We'll meet this line at point Q. This is point Q. Alright, and we extend this line and meet the line y equals x at point R. This is the meaning. Draw a horizontal line from P to meet the line x equals alpha at Q and y equals x at R. Like this, from P horizontal to meet the line x equals alpha at Q and continue meets the line y equals x at R. So what is the coordinate of this point R? Alright, so this point R will have coordinate with x2. This is x2. Okay, this is x2. Just now, first approximation is x1. So this is x2. And the y coordinate, x is x2. Y same, right? Same like this one, right? So y coordinate will be gx1. Because horizontal line ma. So same lah. Okay, right? So let's do the next step. If the slope of the curve at x1 is less steep than the slope of the line y equals x, means here. The slope here. The slope of, if the slope of the curve at x1, yes, this one, is less steep than the slope of the line y equals x, means less than 1 lah. Line y equals x, the gradient is 1, equals 1 ma. So the question say if the slope at this point P is less than this, means modulus less than 1 no? Okay? But I think my curve is not good. It's okay. Later, I think the next one we will see already. Okay, so draw a horizontal P. Okay. Then means that G prime X less than 1. My line can see actually G prime X more than 1. But doesn't matter. You imagine it is G prime X less than 1. Okay, just imagine. Okay, my curve is not that good. Then QR should be less than PQ. Means this distance QR should be shortened compared to PQ. Should be shortened. Let me see. I think can. Should be shortened because mine, as I say again the point that I choose is not that good My curve, the curve I draw. So go back. You can try You can try. You sketch your curve more like this. Okay. Then you choose a point. Then you will see better. You will see that the first step actually this distance already shortened than this one. my example now is not that good lah. So you will see that this distance is actually shortened to this one. If you can choose a point where the tangent is like more slant, all right, less steep. That is x2 is closer to alpha than x1. Means that this x2 suppose is closer than x1. All right, no lah, it's not good. Okay, never mind, I draw another one. Okay, to show better. All right, I draw another one, so that we can have yeah, better view. Okay, hold on, give me some time. Okay, axis, y, x, 0. Okay, this is a line, y equals x. All right, remember y equals x, the gradient is 1. Okay, so the curve is like this. I draw a curve like this. Okay, so this is y equals gx. All right, let's say point, let me see. Okay, so this is the line, this is a root law. This is a root, which is x equals alpha. All right, okay, then I choose a point P here, let's say. This is point P with coordinates x1 and gx1. All right, with coordinates x1 and yeah, you know that the y coordinate is gx1. All right, I think this is better. Okay, so you see that the slope at this point, you see like this. Of course, the value is negative, but we want the modulus ma. Remember just now we say the modulus of g prime x less than 1 ma. Okay, so you see that this is actually less steep compared to the line y equals x. Can see lah, it's less steep, so that the gradient, the modulus of this gradient is less than 1. Definitely less than 1. Now can see, Okay, so we continue the step as we should say just now. So we will, from P, we draw a horizontal line to meet the line y equals alpha at point Q. All right, then continue to meet the line y equals x at point R. All right, so the coordinate for point R will be x2 and gx1, right? Because it's a horizontal line, so the y value same, which is gx1. Okay, but different x already, right? So we name it as x2. So the coordinate for point R is x2, gx1. X2 and gx1. All right. Now you can see very clear. Because the slope at point P, the gradient of the tangent, the modulus is less than 1. Therefore, you will see that definitely QR is less than PQ. Can see, right? The distance QR is shorter than PQ. All right? This is clearer. All right? Why this happened? Because of this. The gradient of this curve, the gradient of GX at point P is less than 1. All right? Means that if you sub this x1 into the g prime x, you will get that the modulus of this gradient is less than 1. So if this happen, then when we extend a line like this distance of QR definitely shorter than PQ. All right? So this means the x2 is closer to the actual root. Right? Because this distance is shorter. So definitely x2 is closer to the actual root compared to x1. Okay, right? So come back here. So we will say that x2 is a better approximation to the root. Means that it's closer and closer already. Alright, so next, remember just how we say the iterative method is actually a repetition process. We repeat. So we are going to repeat the process, you see. Okay, next, we are going to repeat the process like, okay, since coordinate R is x2, gx1, right? Just now we already say. And this point lies on the line y equals x. Okay? Point R lies on the line y equals x. So the coordinate for point R is x2, gx1. Okay? and this point lies on the line y equals x, means the x coordinate and the y coordinate are the same. So if they are the same, so we get this relation, x2 same as gx1. See that? This is how we get this relation. Means when we have x1, we can sub x1 into the g. So the answer will be our second approximation. Yes, this is the iterative formula. Okay, next, let's see, we continue. So remember how to get this? Now, we extend the line x equals x2 and meet the curve at point x. Alright, so means that it's like this. From R, we extend the line x equals x2 and meet the curve again. Here. We continue this line and meet the curve again at point S. Alright? And name it as point S. Okay, with the coordinate. So the point S have coordinate x2 lah. Okay? And what is the y coordinate? Here lah. Okay, so the point is G x2. Right? So it's G x2. So the coordinate for point S is x2 and G x2. Alright, then we repeat the step again. Draw a horizontal line from S to meet the line y equals x as t, and with this coordinate. Okay, so draw like this. From S, draw a line to meet the line y equals x again, and we label it as point T. Here, point T. Point T lies on y equals x. So what is the coordinates for point T? So from T, we draw down and get our, draw down here and get our x3. See? And get our x3. Alright? So the coordinate for point T is x3, but what is the y coordinate? Same as x, right? The y coordinate same as x, which is gx2. Alright? And from here you see, x3 here is even closer to the actual root. Right? X3 is even closer to the actual root. Right? Therefore, from this relation, because point T lies on the line y equals x, means that the x coordinate and the y coordinate are the same. Therefore, we can get again this conclusion. This one and this one same. So x3 same as gx2. Because this point lies on y equals x, so y and x are the same. So we get this relation again. See that? We repeat the same thing. So if your graph is big enough, you can repeat. So from here, but this one cannot already because you cannot meet the curve again because the curve going down. So this is the closest root that we can get for this example only. Because if we extend this one, just now remember, can we go down here from T, we go down here and then we draw again, and you will get something closer and closer to the actual root but my graph is already small enough, so cannot. Okay, if you want to continue a repeat means from T we're going to draw a line, meet the curve. Alright, then from this point we're going to draw a line to meet the line y equals alpha and the line y equals x. So you see very close already it's already very close. To get the next root, it's very close to the actual alpha. This is a process that we are going to do when you repeat the process, so you get the value of x which is closer and closer and closer to the actual root. Okay? Alright, now we see. So you see, the process can be repeated to obtain a sequence of approximation. Means this one. From x1, you get x2, you get x3, and following. So a sequence of approximation. And hence, the iterative formula is xn plus 1 equals gxn. What is the n? N sub from 1, 2, 3, and following. Okay? Now, means if n is 1, then we get x2. If n is 2, we will get x3. When n is 3, we get x4. Just like this. See? When this is 1, we get x2. We sub x1 into g, we get the second approximation. When we get this second approximation and sub into the G again, we get the third approximation and repeat the same thing. All right. So this example show you very clear how we obtain this formula. This is what mean iterative method. All right. Okay. Then you see that the iterative formula is used repeatedly with x1 as the first approximation to find x2, x3, x4, and so on, until the root to the required degree of accuracy is found. It depends what the question give, what the instruction of the question, how you want to stop. Later when we see question, we will discuss this. All right. But we have to be careful of these three conditions. Also important. Number one, the rate at which this approximation converges to the root alpha depends on the value of g prime x in the neighborhood of alpha. Means how fast it can approach closer and closer. Like the example that we showed is quite fast. At first, x1 is quite far from the alpha. Second already very close. And the third one, closer and closer. Okay? So this rate, how fast we can find the approximate value of x, which is very close to the actual root alpha. It depends on the value of g prime x, modulus modulus value of g prime x. Means we don't bother whether the tangent is slant like this or slant like this. We just want the value. That's why you put modulus. Okay, so number one, the smaller value of g prime x, the modulo of g prime x, the more rapid of conversion. The smaller of the first g prime x, means the line is very close to horizontal. Okay, the faster we can get the root which is very close to the actual root. All right, and C, the method fail if g prime x more than 1. Okay, if g prime x more than 1, the method fail means you won't get the approximate value of x which is closer and closer to the root. You will get something go further and further from the roots. Alright, that's why the condition to use this iterative method, the condition is the modulus of g prime x must be less than 1. If more than 1, the method fail. Alright, let's see two examples. What is the meaning of the method fail? Okay, like this. Alright, let's make it bigger. So I can show clearer. Okay. Alright. So you see, the first example, where this is the actual root. This is the actual root. This is our first approximation, x1. Alright. So you see at this first approximation, this point, you see the tangent? Yeah, the tangent is very clear, is less than 1, less than this. This is y equals x. So you see the tangent at the first approximation is like this. More horizontal. So definitely the gradient of this is less than 1. Alright. So if this gradient of the tangent less than 1, you see the approximate root is actually, by using the method that we explained just now, the approximation is actually closer and closer and closer to the actual. Alright. Let's look at the second example. You see? Second example. This is the actual root. This is our first approximation here. Alright, our first approximation is here. So you see this, the tangent of the curve at here. Yeah, you can see it's quite steep, right? This tangent is quite steep. So definitely the value of g prime x, or the modulus of g prime x is more than 1. Okay, so when this happens, you see, when we use the iterative method to get the second root, meet the line x equals alpha and meet the line y equals x. So we get the second approximation. So you see this second approximation is actually further from the actual root compared to x1. This is what we mean fail, because when you continue, it will go further and further and further, but you cannot find the value which is approaches to the actual roots. Okay. So as conclusion, all right, so when we want to use this iterative formula to find the approximate roots, all right, so first thing we have to see the value of g prime x1. All All right, the modulus must be less than 1. Then only we can use. All right, so if this happen, then just apply the formula to find the second approximation by just sub in your x1 into your g. This is g prime x, this is g. Okay, then we get the third one by subting this x2 into the g, and so on. All right. Okay. So this is the concept of iterative method. All right, now we will see two examples in the textbook, example 3 and example 4, page 1475. We are going to discuss these two examples, then exercise 6.1, then there is one past year question for iterative method, all right, which is 2015. Okay, so let's look at the textbook. (175). Here. This is a complete example, so let's make it smaller. Okay. Okay. All right. You have your textbook, right? You can refer to a textbook also if you want. You see, this is how the this is how a question can be asked, which is using the iterative method. All right, so you see the question says, show that the equation x squared plus 4x minus 1 equals 0 has a root between x equals 0 and x equals 1. This is what we have learned yesterday. First, you're asking to show that there is a root lies between here and here that we have learned yesterday. Then using an iterative method to find this root correct to 2 decimal places. Okay, this is the hints that tell us where to stop and when to stop our calculation. All right. Okay, so first step, to show that there is a root lie between x equals 0 and x equals 1. Remember, we have to find our FA, FB. So first we make sure you rearrange your equation so that all the terms to the left hand side and right hand side only 0. So we let the left hand side become our fx. So let fx equals x squared plus 4x minus 1. So sub in 0 or sub 0. So 0, 0, so f0 is -1. Then sub in 1. So 1 plus 4, 5. 5 minus 1, 4. So positive. Show these two values. But remember yesterday I asked you to show don't just show the value only. Show the calculation. Then you write the conclusion. Since the multiplication of f0 and f1 is negative. Or you use the sentence, since f0 and f1 has opposite sign, different sign, remember? Then there is a root lie between x equals 0 and x equals 1. This is what we have discussed yesterday. So why we want to do this step? Because we want to choose our approximate root. We want to choose our initial approximate root, the x1. All right. So first we have to rearrange. Okay, hold on. All right. So you see, I see what the x1 that they choose. They choose the initial is 1. They choose this one. Okay, but for me, how we choose the first one, because the question never give us. For me, okay, you know that the root is when fx equals 0. So you see these two values, which one closer to 0? Or if you draw the graph, okay, when x equals 0, f is -1. This point. Okay, when x equals 1. When x equals 0 is -1 here, this point. Sorry, this point. Okay, and when x equals 1 is 4. When x equals 1, it is 4. Let's say 4 is here. So this point. Alright, this point, like this. Okay, so the curve is something like this the curve so this is a root. See right? When x equals -1, when x equals 0, y equals -1, this point. Alright, when x equals 1, y equals 4, this point. There's one up, one down. So the curve like this is definitely cut the x-axis at a point. Therefore, we say there is a root lies between 0 and 1. Okay, and you see that the root is when fx equals 0. So you see which value closer to 0? This one closer to 0, right? This one, the distance from this point to 0 is only 1 unit. But the distance from this point to this one is 4 unit. So it's actually x equals 0 is closer. Alright, so if you have to choose yourself, then please choose a value of x which is closer to 0 lah, where this value closer to 0. Okay? But for this example, they choose this one lah. Doesn't matter. Okay? So you see, first step, we have to arrange our equation, okay, into this form, right? We only left x at the left hand side or shift to the right hand side, right hand side, yes. But we actually have different method to shift it. You see, this example show you two different methods to shift it. First, he factorized x squared and 4x. Now he shift. So minus 1 shift here, plus 1. Then x plus 4 shift here. So you see, left hand side x only, right hand side is a function in x. So this is x, this is gx. This is one of the method that we shift. Okay, another method, you can shift like this, you see. X squared plus 4x minus 1. So he shift minus 1 and 4x to the right hand side. Okay, then x will be 1 over x minus 4x. Means shift 1 more x here. Shift 1 more x here over 1 over x. So 1 over x minus 4. Okay, we don't use square root lah. We don't use square root. Okay, so you see, even arrange in this form also, we have different way to arrange. Later we will tell you. Okay, later we will see which method is better. How to move it is better. Okay, so next we apply the iterative formula. Remember xn. Xn plus 1 is g xn. Right? We are using this formula. Okay, so consider this. Then initial guess, as I say lah, they choose 1 lah. Because we know that there is a root lies between 0 and 1. So they choose 1. Okay, fine. So you see, so they don't use x1, they use x0. Also can same lah. You want to start from 0, you want to start from 1, up to you. Alright? So if the initial you want to write as x0, then the following will be x1, 2, 3. If you want to start with x1, then the following will be 2, 3, 4. Okay? But normally lah, honestly, we practice x0 lah. Alright? We practice x0 equals 1. Okay, so our x1 will be sub 1 into this formula. So it's 1 over 5, 0.2. Okay? Then this is x1. So sub this x1 again into your function. So I get 0.2381. So remember just now the question say to 2 decimal places. Doesn't matter they want 2 decimal places or 2 significant figures. Remember, in your calculation, always 2 more than what the question want. If the question asks for 2 decimal places, in your calculation, please calculate and write up to 4 decimal places. Alright? If the question wants 2 significant figures, then please, in your calculation, you have to write at least up to 4 significant figures. Alright? Always 2 times more than the question one. Alright? Let's say if the question wants you to write correct to 3 decimal places, means here you must write until 5 lor. Understand that? Okay, so 4. Then again, sub x, this x2 into the gx again, and you get this. You see, I still use 4. Okay, so this is my third approximation. So the third approximation again sub into the gx, I get the 4th. Okay, you see, then we will ask, when to stop? You see, we never repeat. No, there is no same answer yet. So we will stop until we get 2 consecutive answers which are the same by using this number of decimal places. So you see, when I sub in 0.2361 again into my gx, after convert to 4 decimal places, yes, you see, I get the same answer already. Until I get 2 same answers, then I stop. Then we can stop already, and we make the conclusion. Thus, the required root is 0.24. Only this part we follow what the question required, 2 decimal places. Then we convert. But when we are going to stop, if this is 2, then we have to use 4 until we get 2 answers in 4 decimal places exactly the same, then only we stop. But you can see lah, the answer is closer and closer to something, right? Okay, so this is the first derivative formula that we use, so we get this answer. So they even show you the graph, you see. Sorry, I forgot to move up. Okay, I forgot to move up. But you have your textbook, right? I hope you see from the textbook lah. Okay, I hope you see from the textbook lah. Okay, that how we calculate. Okay, how we calculate. All right, you see from the textbook. Okay, how we calculate. As I say again, because the question 1, 2 decimal places, so here must be at least 4. Then sub your x2 into the function again and get another. Sub in your x3 into the function again, you get this one. So there is not same yet. So when I sub this one again into the gx, yeah, you see, I get 2 consecutive answers which are exactly the same by using 4 decimal places. This is how we can stop. Here we can stop, then we make the conclusion. Therefore, the required root is 0.24. Only this part, okay, we convert to what the question wants. Alright, so you see that even show you the graph, like what we have discussed just now. Okay, this is the actual root. So we choose the first root is here, 1. Hold on, let me see. Okay. They choose the first root here. Okay, so you see when we go up here, we get something here. Sorry. No. I see wrongly. Sorry. This is the first initial root that we choose, 1. That's why you see, this is the actual root. X equals 1 actually is further than the actual root, whereas x equals 0 is closer to the actual root. You see that? So it means that if you choose the initial here, cannot see. Okay, if you choose the initial value here, if you choose 0, we will get this answer faster. We will reach the answer that we want faster. Alright? Okay. Alright. So you see, this is the initial root that we choose. So by using the concept that we have learned just now, cut here, okay, and cut here to get the second approximation. Okay, but also is already closer to the actual root compared to this one. Right? Then go up to the curve. Right? Go to the line. Then we get our next. You see, even closer. Alright, so from here you see, go down. Okay, here. So the third one, you see, when come here, then you cut here. This one touch the curve, then cut here. So you get the third one. You see, the third one, x3. Even closer. Then go up again. Go up again. Repeat the same step. You get something even closer and closer to the actual roots. They should even show you the graph, right? Okay, next, this one. Okay, sorry. Here, remember just how we say we can rearrange in the form x equals gx by different method. So just now we have discussed this one. Okay, what happened if we arrange in this way? Alright, what happened? Okay, let's see. Here. Okay, so if we use the second one, alright, and again we choose the initial one is equals 1. So we sub x equals 1 into our gx, you get -3. Alright, then sub -3 into our gx again, you get this. Alright, then sub this one again, you get this. Then sub this one again, you get this. Alright, then sub this one again, you get this. You see? You get this. But it's approximate like, so until you get again 2 consecutive answer which is the same. Okay, which are the same, then we can stop. Therefore, the given root is -4.24. Alright, so why this one also can? Why that one also can? Remember the original function here? Remember this original function? It's a quadratic function, right? If quadratic equation means it should have 2 roots. Yes. So just now this first arrangement, cannot see. Okay, just now this first First one actually give you the first root. And the second one, this one, actually give you the second root. Yes. So you see the textbook, you see that they show you the actual graph. It's supposed to have 2 roots. Alright? So can I? So why we have different way to arrange it into x equals gx? Because the equation have more than 1 roots ma. So different arrangement give us different roots. So sometimes they won't ask you to find all the roots. Sometimes they just want you to find one of the roots. So you have to choose which one is going to give you the actual answer. Alright? Okay, the next example. Example 4. Oh, sampai sini. Okay, so let's see the next example. Also quadratic. Alright? Use the iterative formula to show that this equation has a root near x equals 1. So they give you the initial value of x that you should choose already. Alright, which is here. Okay, so this one you don't have to show that the roots lies between what lah. They already straight away give you this. Alright, then again we can rearrange this equation in 2 different ways. Or this one sorry, it's x cubed. It's not quadratic, it's x cubed. So they arrange it in this form. Alright, cube root we can use lah. Square root we don't use. Why? Why square root we seldom use? Because it has plus and minus, right? If square root we have plus and minus, so we avoid that. Cube root can. If the root is odd, then we can. Okay, so use the respective iterative formula as we say. X naught is 1. So sub 1 into the formula, you get this. Sub x1 into the formula, you get second. Sub x2 into the formula, you get third one, fourth one, and fifth one. Alright? So you see from here also, because just now the first example, first time, so we write everything in clear. So in exam or when you do exercise, you only need to show this, substitute the value into the gx at least twice lah. At least 2 times you show this step. Then after that, you can just write the answer. Or you can key in this formula into your calculator and press calculate, remember? Just press calculate. Okay, but show at least twice. Then the following, you can just show the answer. So you see, from this formula, you see the value is not approached. 1, then go to 1.5. Then suddenly, more than 1. Then suddenly get something less than 1. Then go back to something more than 1. Then go to something less than 1. Then go to something further again from 1. Further and further again from 1, right? So see or not? So therefore, we see that this sequence of the value of x do not converge. Do not converge. Alright? So means that this iterative formula cannot give you the answer. So it means that, remember just how we say, to determine whether an iterative formula can get the answer or not, depends on what? Yes, depends on your g prime x. You see, let's check this equation. Okay, this is gx, right? This is gx. I differentiate it. Remember how to differentiate? Coefficient in front, differentiate 4, 0, differentiate negative x cubed is negative 3x squared. Then I sub my first initial. Just now we say the first initial is 1, right? You see, I sub 1 into the g prime x. I sub 1 into the g prime x. I get 3 over 2. The modulus is more than 1. See, 3 over 2 is bigger than 1. That's why when you use this iterative formula with this initial number, you cannot get the answer. See that? This is how important the value of the modulus of g prime x is. It's supposed negative lah. It's supposed you get something negative. That's why we want modulus. Okay, that's why we want modulus. So it's 3 over 2. So it's more than 1. So this formula cannot be used. Alright? So this example is good that we related to the concept, the basic concept that we have learned just now. Okay, alright, let's see the second one. See? Yeah, the second formula, this one, cube root of 4 minus 2xn, right? Okay, again, start with x naught equals 1. So sub 1 into the formula, I get cube root of 2. Then sub cube root of 2 into the formula again, I get this. So remember I say at least sub in twice. Then the third one, you can just repeat the answer. Alright, so 1.198, 1.170, 1.184. You see that it's actually approaching to something. Even though big, small, then big again, then small again. Right? But you see, even big, small like that. But it's actually approaching to the actual root. Alright? Until we get two consecutive, the same. So this one cannot stop yet. Because I can't get two consecutive. But why they stop? They actually round up this one to 2 decimal places. When you round up this one to 2 decimal places, yeah, you get this one lah. But remember just how I say? Yeah, we must get at least 2 consecutive 4 decimal places same. Then only we can stop. Alright? But it's okay, right, for you to write more because you already key in this formula into your calculator. You just press calculate only. This example is a little bit not perfect lah. They don't show the actual step that you should do in STPM. Okay? The example just show you how to solve. They don't show you what you should do in STPM. So please remember to answer in STPM what you should do. Okay? So the following, you have example 5. Then that one, okay lah, not difficult. You read yourself. Okay? Please read yourself your example 5. Okay? Alright, so I give you a small break. Alright? So that you can go through again the notes, digest a bit. Alright? So the next video only I show you how to answer exercise 6.1 and the past year question. Alright? You go through the notes again and digest first. Alright? Okay, we continue later.